Okay, Kaido, I believe it's you and then the lunch. So how do you feel about it? No, we don't, but we have you, so we need to hear what you have to say. So Kaido is a person with specific interest in peatland and forest matters, of course, and specifically greenhouse gas exchange and carbon and nitrogen balance and so forth and so forth. So the floor is yours.
Thank you. When I initially heard that one presentation was missing, I hope that I have more time, but it seems that I don't. So my name is Kaido Soosaar. I'm from University of Tartu, and actually I would like to acknowledge practically the whole team of Life for OrgBalt, because we did a lot of field works to collect that amount of different data. So my presentation will focus on methane and N2O, and I wanted to highlight why methane and why N2O. Probably not all of us know what is the difference between different greenhouse gases. And the methane is actually 28 times more stronger greenhouse gas than CO2. And not lately, but after the pre-industrial period, the concentration of methane has doubled. However, CO2 concentration is increased only 30%, let's say only. And methane is responsible about 20% of the global warming potential. And if you think about N2O, N2O is even more potent greenhouse gas. It's up to 265 times more important or more dangerous greenhouse gas. And if you think about the anthropogenic sources, it's like 40% is coming from there. And the impact of drainage is not so well considered in the inventories. So this is a topic which we need to study a bit more. Jyrki gave a very nice overview about the methodology, what we did, and I will focus mostly on the gaseous soil methane N2O flux, marked red. And I was thinking that as a scientist, I would like to give more like scientific background why we have this kind of results. So I will go a little bit into the processes. And so we think about, we have untrained peatland, and we think about methane cycle. So all the work is done by different microbes. And if we have water level high, then we have this kind of microbes called the methanogenes. So it happens methanogenesis, which means that there is a methane production. And then when we have the methane in the soil, when we have a release through the soil to the atmosphere, but there would be also a source from plants. Small plants, different ones, there could be the emission rates could be different, all depends on the plant physiology. And now if we drain the peatland, when we lower the water level, this means that there are other microbes start to work. And when we are lowering the water level, we are giving oxygen into the soil. And doing that, we are activating methanotrophs. These are the group of microbes who are oxidizing methane. So the soil methane balance finally depends on the ratio between the work done by the methanogenes and work done by the methanotrophs. If you go to the N2O flux, this is, I would say, very tricky and very difficult. I would like just to highlight the two main processes. One is nitrification, other one is denitrification. And what is important regarding N2O, you know that there are many studies which showing that the N2O flux is coming out as a peak. There are peak fluxes. So to have a high flux in N2O, you have to have very certain conditions, have to be filled. For example, you have to have ammonia in the soil if you have an aerobic condition. And then if you have ammonia in the soil, then happens the nitrification. And during that process, the ammonia will be converted to nitrate, and then we have N2O. And then if you have a lot of nitrate in soil and nobody is using that nitrate, and then there is a rain or there is a heavy precipitation, or we are in some reason lifting the water level, then the other microbes start to work, and then we have the denitrification. And then happens the conversion from nitrate to N2, and there could be a byproduct as N2O. So what you remember here is that if we have dry soil, then we have nitrification. If we have wet soil, then we have denitrification. But if we have, like in the middle, both processes can happen at the same time, and we can have continuous flux. Now a little bit about our objectives. So the main idea was to estimate the annual fluxes of methane and N2O, as well somehow try to explain those fluxes, and then finally to determine the country or region specific emission factors. And we did a study, as we know, that Estonia, Latvia, and Lithuania, and they also included some similar studies which the Latvian colleagues did during previous projects. And we also focused on different tree species, downy birch, Norway spruce, Scotch pine, black alder. And then we also studied the drained grasslands and croplands. And maybe the method is, yes, we already last presentations explained it with, we did the manual measurements, collected with those white chambers as you see on the left bottom figure. And then we measured the methane and N2O concentrations with a gas chromatography. And in addition, we also measured different environmental parameters like soil temperature, air temperature, moisture, water level depth, and also did soil water chemical analysis and soil nutrient content. But actually, we also did the microbial analysis. So we a little bit know, I'm not going to talk about the microbial composition in this study, but we also wanted to go a bit more deeper, just really explain what's going on in the soil when we have higher fluxes or we have some consumption of methane. And here is the forest sites. Altogether, we had 25 sites with different tree species, as I mentioned. We have very nice coverage over the whole Baltics. Most of the sites, even though we're in Latvia or from Latvia. And here are the results from forest sites. We see that upper graphs are temperature dynamics. So if we have a higher temperature during the summertime, and we also have higher N2O flux, but it doesn't mean always like that. And as we have drained soils, and as you remember that I mentioned you that if the water level is down, then we have those methanotrophs who are eating that CO2, that methane. So we have methane consumption. So what we see that most of the time the methane was below zero, which means that all of our ecosystems were consuming methane. In this figure regarding N2O, even though we see some kind of temperature dependence, like we have higher in summertime, but N2O is actually a very interesting gas, and it could be also emitted during the winter time. Then there is a freezing thawing moments, there are different conditions, and the limitation of quite many studies is that people do not do the measurements during the winter time. But in under this project we did. So we had each month we went out to do the measurements. And here is some annual values you see on up left, marked with A. We see the methane is annual fluxes in all of the sites were negative, which means all the sites were methane consumers. On the right up, you see also the relationship with the soil water level. And what we found out that if the water level is below 25 centimeters, all the methane what is produced in deeper zone will be oxidized, and the ecosystem will not be the methane producer. In case of N2O, on the left bottom graph, we see that some of the sites are very high emitters. So it's showing that the site, the way you do your measurements, it's very important. There is the local conditions could vary a lot. And if you compare these with in the middle bottom is the undrained sites, we see that the N2O flux from the drained and undrained side is significantly different. We have more from the drained sites. As you remember, I mentioned you that there are nitrification, denitrification microbes who are liking this kind of pulsing water level. They want that water level is up. Then we had there is anoxic conditions, so the N2O can produce during denitrification, and then if you're going down, then the other microbes start to work. Now, this is a comparison of what we got compared to the IPCC default values. As Aldis mentioned, the temperate and boreal zones, this is also very important actually. So in Estonia, for example, is partly between the boreal and temperate zone. We could call it as a hemiboreal. And then temperate zone is very wide, so it could be maybe too different for us. I mean, too warm conditions, maybe in the southern part of the temperate zone. But we see that in our case, all the forest sites were methane consumers, and in the same time, IPCC emission factor is positive. And in case of N2O, there is no significant difference. So the fluxes are for the Baltic states in average in the same range as the IPCC default factors. But if you see the Estonia, Latvia, and Lithuania separately, you see that there is a very large variation. In Estonia, there is the lowest, and in Lithuania, there is the highest N2O emission. But in the same time, I would like to highlight that it's very important if you have seen this kind of high emissions that it could be due to the one specific site. It's not like the Lithuanian forests are larger N2O emitters than Estonian. So to have more, to have better results with less uncertainty, we have to do more measurements. We have to have more forest under the study. Now about the grasslands, those we also had a nice coverage over the Estonia, Latvia, and Estonia. The total number of sites were 10. We had 7 grasslands and 3 undrained peatlands as a comparison. What I would like to highlight, what I also mentioned during the last previous slides, that here is an example, just random examples of N2O dynamics, annual dynamics. And as you see that the red line is the N2O flux, it's going up and down. And for example, if you see the left, the highest peak is only one time when we were out, and next time the flux was down. So it's very important to go out as often as possible. In this project, we in some cases went out once per month, in some cases twice per month, all depended how many resources we had. But I would say that to have a proper results, one should go out every week, or even use eddy coverage systems or some automated chamber systems. So manually we cannot get those peaks, and in just the opposite way, as it could happen also, that we are going out and we have high flux, and then we think that the high flux is always there, but actually it's not always there. And if you think about the grassland soil N2O flux, there is also, as you see, very high variation from -8 till 680. And if you look on the methane, it's also minus 87 up to 11,000. So you know that in our region we have winters, we have snow, and when the snow is starting to melt, this means that the water level can temporarily go up, and this can enhance methane production, and then we have high peaks. So, but it could be only once per month, a very short period during a year. So this is the PCA analysis. I brought it in just to explain that it is, if you talk about CO2, and it's quite simple to, well, not simple, but there are quite good models to model CO2 flux, because CO2 is dependent on the temperature and soil moisture. But if you look in N2O, there is practically no model available with what you can model N2O flux. There are some, of course, there are some models, and people are trying to improve it, but there are so many different parameters which are influencing the N2O flux. Is there nitrate enough? Is there water level at the same time high? Is the temperature high? But if you have temperature, the water level high, but we don't have nitrate, we have ammonia. There are different combinations. And then the comparison with the default emission factors. See, there is some kind of mistake. So what we found out that the N2O flux was in our case lower than the emission factors. But in case of methane, we see that we are in the middle of the boreal and temperate zone. So in temperate zone, nitrogen-rich peatlands, we see that 16, and the boreal is 1.4, but we are somewhere in the middle. And one slide about the croplands. So far, the inventories haven't include methane flux from those ecosystems. In our based on our study, we see that it's minus 0.6 kilograms per hectare per year. So our croplands is also where the methane consumers, and in case of N2O, it was fitting in the same range as IPCC default factors. And the last slide, so conclusion, as I mentioned, forest lands in our case where all of them were methane consumers, but it doesn't mean that all the drained forests are the consumers. It depends on the drainage, how effective is the drainage, is the old reconstructed drainage, and so on. So the climate zone is important. As we see, compared to temperate and boreal, we see that there is a significant difference. And can you bring the line where is the boreal and now starts the temperate? So it could be debatable. So which emission factors are more suitable for our region? And soil nutrient status for sure is important. In our case, we are focusing on nutrient-rich soils. As you saw, the water level, as I mentioned, the processes, the water level is a key factor. Even though we are measuring the water level, the key factor is actually oxygen content. But as oxygen content is very hard to measure, then we always relate the measurements with the water level. And we hope that this study can be, the data from this study can be used in the tier 1 or tier 2 methodology. And we do hope that we have some continuation of this to this project, and we can continue have more precise and less uncertain data. So thank you very much.
As we are 20 minutes into lunch break, shall we address just 3 questions, perhaps? Let's do the voting now. I mean, let's rank these. So the more likes the question has, the upper it goes. So let's spend 30 seconds for that. So you can like your question and somebody else's if you want. All right. So what do we have? A question by Enars appears to be the most popular. So if we have negative methane emissions, can we consider drained organic soils are lowering atmospheric methane concentration?
No. The thing is that
I like the pause. I like the pause. I mean, lovely.
Well, in theory it does, because if you think about that is negative, this means that it should lower it. But if you think about other sources, the other sources are so large, so that small consumption by these ecosystems are actually not so important. And in addition, if you know the future climate predictions, we will have more precipitation, which means that the soil will be a bit more wetter, which means that the consumption of methane is there are some studies which are showing that it's actually decreasing in time.
Okay, so what's your reaction? It's more like a comment. We should mention that methane is a relatively short-living greenhouse gas in the atmosphere, different to CO2.
Yeah.
Undrained peatlands reach an equilibrium and not heating the climate. Yes or no?
I was agreeing with the first part, but the second part was undrained peatlands reach that. Well, no. Well, we shouldn't look only one side of the coin. We always should look at a wider picture. So we cannot talk only about methane. Yes, regarding methane, it is climate cooling, but if you think about peatlands, and if you have drained peatlands, we have loss of the carbon in soil. If it's nutrient rich, and then we have some kind of precipitation moments or flooding moments, then it's also a large source of N2O. So I wouldn't agree with that.
All right. Okay, so the last one, the top one.
Yeah. In drained peatlands, you have large open water like ditches, which emits considerable methane. Well, no.
Again?
And the reason is quite simple. We were focused on drained sites, so our focus wasn't so much the natural peatlands. Yes, we had some undrained sites, and in that sense, in theory, so we think about natural peatlands, and the water level is high, and where is the methane? Methane is in the water. And the water is, the gas is moving. It's not like we have wet open area and then we have in that spot we have higher methane concentration in the water, and next to that we have lower. There, in theory, there could be so, but I don't know exactly. What I do know is that in peatlands it's more important is the hummocks and hollows. So we have higher patches of plants in the open peatlands, and those are different than the hollows where we have higher emissions. And this is important, but the open bodies, I don't know the answer.
Oh, you should have started with that. I mean, to make it shorter. Just kidding. Okay, Kaido, thank you so much.
Thank you.
Let's move on. And I believe you can catch Kaido in the lunch break and ask you a question if it wasn't addressed. Before you go, please, hungry people, before you go, a few things from my side. So for those who are a bit concerned about tomorrow's plans and didn't get the message, at the registration desk, you can get all the information about what's happening tomorrow. Okay, so that's one thing. We meet back at 2 p.m. sharp. I mean, please come a bit earlier because at 2 we start. Also for the online audience, so 14 hours. It's the when we start after the lunch break. You have poster session, which is just to that side towards the lunch. I mean, lunch and posters could be combined. Networking, getting to know, and so forth. But before we go to posters and before we go to the lunch, we should make a joint photo. We have Matis, the photographer. Yes, yes. Okay. So I think, use that door because that direction we have a big staircase leading towards the second floor. So on that staircase, we'll have a joint photograph. So make sure you see the camera. That's the general rule in group photos. So let's use that door and go towards the area of staircase and we'll do the photo. And then you're free until 2 o'clock and we meet back again in this room.